Hello everyone, thank you all for being here. And on behalf of all the people shown here, I would like to thank organizers for organizing such an amazing summer school, and also to thank Adam Leroy and Annie Hughes for great support and input throughout whole time of being here. In next 6 minutes, me and my colleagues are going to present the project we've been working on over the last 2 weeks, and it's about rotation curves and mass profiles nearby galaxies. Firstly, we are going to list all the main goals of our project. Then we're going to introduce the data set we used. Moreover, we are going to present the methods we performed in order to get results. And finally, we are going to show some nice results to all of you. So let's start. So we had two main goals of our project. The first one is to investigate how three components are distributed across the galaxy. And we are having three components. The first one is the stellar component, then atomic gas component, and molecular gas component. And the question regarding the first project goal is to determine where does the transition from atomic to molecular gas is happening. The second project goal was to derive a rotation curve on the data set we used. And for that purpose, we used velocity maps, and you will hear more of that on the next slide. And additionally, we learned and developed the data, the tools in order to get some results. So the data set we used for the atomic gas component, we made use of H1 21 centimeter line as part of BLA THINKS survey. Then for molecular gas component, we used CO2 maps as part of PANG's ALMA survey. And finally, for the stellar component, we made use of near infrared data, WISE and Spitzer IRAC at 3.4 and 2.6 micrometer respectively. Our pilot target was MTC 3621 with properties are listed here. Altogether with the pilot target, we also derived the rotation curves and mass profiles for all the galaxies listed down here. And on the right side, we can see the data that we used for the analysis, so moment one maps, moment zero maps, and also the near infrared data. And as you can see, a stellar component and atomic gas component appear to be more spatially distributed across a galaxy, as opposed to the molecular component, who appears to be distributed in the central inner kiloparsecs in the galaxy.
The initial step of our analysis was to match the pixel coordinates of the images with the polar coordinates in the plane of the galaxy. To do this, we obtained the inclinations and the position angles for all our galaxies, and then carried out all the required coordinate transformations. Using the obtained coordinates, we sliced the images of the galaxy into beams by galactocentric radius. By processing every ring, we got rotational velocity curve and radial mass and surface density profiles. We applied two approaches for extracting the rotation curve from the beam velocity map. The first option is to compute average velocity, taking into account the angular coordinate. Another way is to fit a very simple frisbee model to every ring. The fitting procedure yields the amplitude which corresponds to the desired velocity. As we see on the right panel, these two approaches give almost identical results. To study the distribution of stars and cold gas in the galaxies, we have computed surface density and enclosed mass radial profiles. First, we made density profiles, essentially by averaging the zero moment mass in every beam. Then we converted the units to solar mass per square parsec and integrated them. The stars and molecular gas have a nearly exponential profile, while the atomic hydrogen spans a wide range of galactocentric radius. From the mass profiles, we compute a formal circular velocity profile for all of the components. For example, for MVC 3621, the atomic gas contribution starts to be quite significant, approximately after 7 kiloparsec.
Here we compare the surface mass density profiles of all the galaxies. The legend is shown in the first plot. For stellar mass, we recover at a more or less exponential profile as shown by the orange curve here, and this is expected for these galaxies. And for all galaxies, we observe a slight depletion of atomic gas, which the blue curves here show towards the central regions. As for the typical transition radius of different gas phases, here will be the crossing points of blue and green curve. We found for half of our samples, the transition happens at around the effective radius, with the exception of NGC 2903, the first one here, 3627, the middle one in the bottom, and 7793, which is the last plot. For 2903 and 3621, the transition takes place at about double the effective radius, whereas there is no such transition in 7793. And in the next plot, here we show the velocity profiles we derive from different tracers. Legend is at the bottom middle plot. Velocity traced by the H1 moment map shows a similar trend for most galaxies, rising steeply at first and then flattening towards the outskirts, except for 3627, which we see a declining rotation curve. And for 3627 and 7793, we also observe that the H2 trace velocity is larger than that of H1 throughout the whole galaxy. And the last slide is just a summary of our talk, and thank you very much for listening.
Thank you. Right. So are there questions about this project? So, are there any, so basically, sorry, so are you online, Project 10? I guess you are. Are there any systematic effects, especially at large, radial distance, due to simply the fact that you're going to very low densities, that you have some contamination from background galaxies? Did you encounter any particular systematic problems?
Indeed, we didn't go to very large values of galactic-centric radius, because that's where our very simple model of velocity starts to break. However, we did try some experiments with removing the background sources from the infrared profile, but we didn't include them in the final results.
Okay. And there is a question on the, sorry, the question was about Project 9, but I think it's wrong, no? I mean, oh, Project 10, yes. So is there H2 to H1 transition in NGC 7793?
In fact, we did not observe this transition, as Leon has said, in 7793.
Okay, thank you.